This video, we solve problem 8 from section 8.5 of the Larson and Edwards Calculus Early Transcendental Functions text, 7th edition. We're asked to evaluate the integral of a rational function, which is just a polynomial divided by a polynomial. And this is in the section about partial fraction decomposition. I want you to notice that the degree of the polynomial in the numerator is degree 3. Remember, the degree of a polynomial is just the highest degree of any term. And if you're talking about polynomials in one variable, the highest degree of any term is just that largest exponent. So this is degree 3 and this is degree 2. When that happens, when the degree of the polynomial in the numerator is greater than the degree of the polynomial in the denominator, we have to use long division before we use partial fraction decomposition. So let's write that down. Since the degree of the numerator is greater than the degree of the denominator, we start with long division. Okay. Now, if I've got a polynomial over a polynomial here, this polynomial in the numerator is going to go over here, and this polynomial in the denominator is called the divisor that goes outside when you're doing the long division. And typically we like to write this polynomial and this polynomial in descending powers of x, starting with the highest power of x. So we've got our x squared term, and then we add an x to the first term, and then we add the constant term. Here, this is a degree 3 polynomial, so we start with our degree 3 term. And then the next thing we would add is our x squared term. But there is no x squared term, so we add in a 0x squared as a placeholder. Then we bring the negative x down, and we bring the positive 3 down. Now, this problem is really not that difficult. If you can solve this problem, 279 divided by 13, if you can solve this using long division, you can solve this using long division. This is handled in very much the same way that this is handled. So if you remember how to do long division with numbers, you can do this. This is really very similar. So let's talk through this, and then we'll talk through how to do this. If I'm taking this 279 and I'm dividing it by 13, I would write it this way. The divisor, 13 goes outside, the 279 goes inside. And I would ask myself, how many times does 13 go into 27? 13 goes into 27 twice. And then we would write that 2 there. Then we would multiply. 2 times 13 is 26. Then we would subtract, bring the 1 down, bring the 9 down, and then we would start that process again. This is very similar, except there are a couple of little differences. Here, rather than looking at the whole polynomial and the whole polynomial, when we start, we're just going to focus on the leading term here and the leading term here. And over here, remember what we did? We asked ourselves, how many times does 13 go into 2? It doesn't, so we skip that. Then we say, how many times does 13 go into 27? Twice. Then we write that 2 down, and then we multiply. So here, what we're saying to ourselves is, or asking ourselves is, how many times does x squared go into x cubed? It's a little bit different thinking about how many times a polynomial term goes into another polynomial term. So I think it's easier if we phrase it this way. Rather than saying, how many times does x squared go into x cubed? I say to myself, x squared times what will give me x cubed? And I can see right away that all I'm missing is an x. I've got an x squared. I want 3 x's multiplying each other. I need 1 more. So x is how many times x squared goes into x cubed. That x will go up here. And I like to write this x to the first term over the other x to the first term in this polynomial. So I'll write it there. Now remember what we did next over here. After you ask yourself that question, how many times does this go into this? Or x squared times what gives me this? Just an x that goes up here. The next thing that you do here is you multiply. 2 times 13 is the 26. We're going to do the same thing, except this time we're going to focus on the whole divisor. We're going to say x times the quantity x squared plus x minus 2. You're going to multiply. Remember, you've got a polynomial here with multiple terms. You'll have to distribute that x. X times x squared is x cubed. X times x is x squared. X times -2 is -2x. And then the next thing we did over here was we subtracted. We said 27 minus 26 is just a 1. So I want to take this polynomial and subtract this polynomial. Well, we all know that when we subtract polynomials, all we do is multiply all of the terms in the second polynomial by -1, and then we collect like terms. So we're going to multiply every term here by -1. If you want, you can add some parentheses. -1 times x cubed is -x cubed. -1 times x squared is -x squared. -1 times -2x is going to make that a positive 2x. You're just changing all the signs. So you change the signs and then you collect like terms in the columns. X cubed minus x cubed is 0. Then 0x squared plus a -x squared is just a -x squared. And then -x plus 2x is x. Then you bring the plus 3 down and you start again, focusing on that first term. You say x squared times what will give me a -x squared. Well, this is an x squared and that's an x squared. The only thing that's missing is the coefficient. So I need to multiply here by -1. That -1 is a term in our quotient. So I'll write the -1 here. And then we'll multiply again. So I have -1, just that piece, times this. -1 times x squared is -x squared. -1 times positive x is -x. And -1 times -2 is positive 2. And then since we're subtracting, oops, sorry about that, having a little issue. Oops. I'm sure that issue will stop very shortly. Sorry, guys. We're multiplying the second polynomial by -1. My goodness, having a little trouble today. Well, I'm not having trouble. -1 times this gave us this. And now we're going to subtract this polynomial from that polynomial. When I do, we multiply all of these terms by -1. -1 times the -x squared gives us a positive x squared. -1 times this gives us a positive x. And then -1 times 2 is going to give us a -2 there. So you're just changing all the signs and then you add like terms in columns. This plus this is 0. X plus x is 2x. And 3 minus 2 is 1. And then we start the process again. We say x squared times what will give us this leading term here, which is 2x. Now I want you to notice that in order for me to get a 2x over here, when I have an x squared over here, I actually have to divide by an x. In order to get the 2, I would have a 2 in the numerator, and I need an x in the denominator so that one of these x's, or this x, would cancel with one of these x's. Because I've got 2 of them over here, and I only want 1 of them over here. If that happens, that tells you to stop. You're done. This is what we call the remainder for this long division problem. This is what we call the quotient. And this is what we call the divisor. This expression here is called the dividend. I'm just going to call it a polynomial. Well, actually, maybe we'll use the appropriate terms. This is the dividend. And before I show you how to write the final answer for this long division problem, let's talk about how to finish this problem over here. So we said, how many times does 13 go into 2? It doesn't. How many times does 13 go into 27? It goes into it twice. You write the 2 there. 2 times 13 is 26. You multiply. Then you subtract. You get the 1. You bring the 9 down. And then you say to yourself, how many times does 13 go into 19? Starting the process over, just like we did over here. 13 goes into 19 once. So you write a 1 here. And then you take the 1 and you multiply by the 13. Gives us a 13. And then you subtract. And then we get a 6. Now, if we wanted to, we could add a 0.0 here and keep going to get a decimal approximation. Since this is an integer divided by an integer, eventually this would terminate. That decimal we would get to a point when we could stop. But that's actually not what we want here. What we want here is a mixed number. So we're going to have this divided by this is equal to the quotient, which is 21, plus 6 divided by 13. And you know that this works because if you take 13 and you multiply by 21, and then you add 6 to it, you're going to get that 279. So it turns out that 279 divided by 13 is 21, and 6 over 13, which is close to 1/2. It's not quite 1/2, but it's close to 1/2. It's about 21.5-ish, okay? But I want you to notice what we did. What we did was we took this, which we call the remainder, and we took this quotient. I'll just label it Q, and this is my divisor. And the final answer was the quotient plus the remainder over the divisor. We're going to do something very similar over here. We're going to have the quotient plus the remainder over the divisor. So our original integrand can now be rewritten in this way. Notice that we have not done any calculus yet. We're just doing algebra to rewrite that integrand so that we can do some calculus. Is the quotient plus the remainder over the divisor. And now, notice that this is a degree 1 polynomial over a degree 2 polynomial. That happened because when I tried to do this operation right here, I had to introduce a quotient. That's actually a clue that it's time to identify this as the remainder and to just finish the problem. But the reason why that is, the reason we ended up here was because we said to ourselves, well, x squared times what will give us 2x. As soon as we got that quotient, we knew that we should stop and call that the remainder. So we've got our remainder, we write that here. We put the divisor down here, and now we will use partial fraction decomposition for this piece, and we'll just use the power rule for these pieces. Now, over here, that will always happen because the division algorithm stops when the degree of the remainder is less than the degree of the divisor. So if you get to this point and you see it, you see that that's degree 1, that's degree 2, I should stop, you can stop. Or if you don't see it, you can say to yourself, x squared times what will give me 2x, and then you look at that and you say, oh, I've got to add a rational function there, that must mean it's time to stop. Okay, so we've got this. In order to do the partial fraction decomposition for this, we want to factor that denominator as much as possible. X squared plus x minus 2 factors in the following way. I need two numbers, or well, first times first is going to give me an x squared. Then here and here, I need two numbers that are going to multiply to give me a negative 2 that add to 1. Now, since the product is negative, that means one of the numbers is going to be negative, the other one will be positive. So what I'm really looking for are two numbers that multiply to give me 2 that have a difference of 1. Well, 2 and 1 will work as long as these have the right signs. In order for the sum to be positive, I need the 2 to be positive and the 1 to be negative. Then negative 1 times 2 will give me negative 2, and negative 1 plus 2 is going to give me that 1. So we're going to have a negative 1 here and a 2 here. And now we'll use partial fraction decomposition for this piece. All right, so I'm going to sort of step away from the integral for a moment. And then we'll get ready to rewrite this as a sum of partial fractions. So first, with my denominator factored, as much as possible, I see that I have a degree 1 term in a degree 1 factor in this denominator times a degree 1 factor. So this x minus 1 to the first will appear in the partial fraction decomposition this way. We'll have a constant over that x minus 1. And since it's just raised to the first, we just get one term in the decomposition. Then we'll add, for this one, it's a linear factor that appears only once. We'll have one term for this one as well. It'll be a constant over that factor. In order to find the values of a and b, we're going to multiply this entire equation by the LCD, and the LCD is always the original denominator. Don't just multiply all of these together. That would give you a common denominator, but you'd have extra factors that you don't want. You want the least common denominator, and the least common denominator will always be the original denominator when you're doing a partial fraction decomposition problem. So we're going to multiply this expression by the denominator x minus 1 times x plus 2. We're going to do the same thing here. And we'll do the same thing here. So let's write down what we did. We stated the form of the partial fraction decomposition. Then we multiplied by the LCD, and then we're going to simplify. Now, when you do, all those denominators should clear. X minus 1 over itself is 1. This divided by itself is 1. Of course, this is as long as that factor is not equal to 0. This divided by itself is 1. And this divided by itself is 1. So this equation is equivalent to the next equation. On the left, we have 2x plus 1. On the right, we have a times the quantity x plus 2 plus b times the quantity x minus 1. Now from here, it's very simple to find the values of a and b by just choosing values for x that will make each of these factors 0. And then we substitute those into the equation, and then we solve for a and b one at a time. So I notice that x plus 2 is 0 when x is equal to -2. So I'm going to substitute x equals -2 in this equation. So let's write that down. We're going to substitute x values that cause each factor to be 0. So on the left, we have 2 times x plus 1. X is -2. And then over here, we're going to have a times the quantity x plus 2 plus b times the quantity x minus 1. I'm replacing my x with a -2. I'm replacing my x with a -2 here. Now, normally I don't show this step, but when x is -2, I've got -2 plus 2 here, which is 0. So I've got a times 0, which is of course 0. So that's the whole point of substituting x equals -2. When we do that, this term is gone, and all we're left with is this equals this times this with an x value in it. So we get a very simple equation that we can solve for b. And let's simplify the left-hand side. This is -4 plus 1, which is -3. On the right, we have 0 plus -3 times b. Divide both sides by -3. -3 divided by -3 is 1. So that was very easy to just solve for b by substituting the x value that would cause this to be 0. Now to cause this function, or excuse me, this factor to be 0, we would substitute x equals 1, because x minus 1 equals 0 when x is equal to 1. So when I substitute x equals 1 here, I have 2 times 1 plus 1, so that's 2 plus 1, which is 3, equals a times 1 plus 2, which is 3, plus b times 1 minus 1, which is 0. Again, we don't often show that step. This just tells us that 3a, or a times 3, must equal 3. So a must be 3 over 3 or 1. So we figured out what a and b must be in order for this equation to be satisfied. Now we can substitute into this expression down here. So I've got this. We said before that that was equal to the quotient, which was x minus 1, plus the remainder over the divisor. And then remember, the remainder we said the remainder over the divisor, excuse me, would be equal to this constant over this factor plus this constant over that factor. A, oops, sorry about that, over x minus 1 plus b over x plus 2. Now that we have a and b, we just substitute them. A was 1 and b was 1. Okay, let's write down our process here. We substituted x values that would cause each factor to be 0, and then we used that to solve for a and b. Then we substitute the values of a and b into the partial fraction decomposition form. And we're substituting that whole function into the integrand. Now we'll antidifferentiate. Now for x, it's just x to the first. We use the power rule, add 1 to the exponent and divide by the new exponent. Dividing by 2 is the same as multiplying by 1/2. Then we'll take the antiderivative of this constant with respect to x. The antiderivative of a constant with respect to x is just that constant times x. And then this piece and this piece requires a u substitution. It's a very simple u substitution. For each of them. But I will write those as a sum of two separate integrals. Notice that there's no integral symbol over here. I've already taken the antiderivative. But there's still an integral here and an integral here because we have not finished this part yet. We have not taken the antiderivative of these terms. So for this first one, I'll let u be my denominator. And because I'm going to have two u's, I'll call this one u1. Let u1 be x minus 1. Then the differential of u1 is the derivative of this, which is 1 times dx. So now this integral can be written entirely in terms of u1 in the following way. Bring everything else down. Then my integral becomes the integral of 1 over, replace the x minus 1 with u1. And then dx can be replaced by du1. Don't let the subscript bother you. It's just a dummy variable. It's a substitute. It's a variable that we're using to substitute for right now, just so that we can get this integrand into the form that we have a basic rule for. You ask yourself, do I have a rule for that? And we do. If this was 1 over x dx, it would be a natural log, right? Natural log of the absolute value of x. The fact that there's a u1 there instead of an x doesn't really change anything, at least not for the antidifferentiation step. So now that we've written this in terms of the new variable u1, we do have a basic rule for that, so we can compute the antiderivative, which is natural log of the absolute value of that denominator, plus c, but we'll just add the c for the last integral. And then the last thing that we do for a u substitution is we back substitute. u1 was actually x minus 1, so we're going to sub that in now. All right, then for the last one, same thing. I'll let my variable, or I'll let my u equal x plus 2, but I will add a subscript of 2 on that to say that this u is different from that u. u2 is x plus 2. The differential of u is the derivative of this, which is 1, times dx. So dx can be replaced by u2, and this can be replaced by u2. So we're going to see an integral that's very similar to what we had here. We still have a 1 there. The x plus 2 is replaced by u2. And the dx is replaced by du2. Antiderivative of 1 over u with respect to u is natural log of the absolute value of u plus c. We're using u sub 2 instead of u. And the last thing that we do is we back substitute. We replace that u2 with whatever it was in terms of x, and it was x plus 2. And that's it. That's that right there. So let's go to the beginning of this problem. If the degree of the numerator is greater than the degree of the denominator, you've got to do long division first. It's a pre-calculus concept. It's okay if you don't remember it. Just brush up. Watch this video again if you need to. Watch other videos on long division with polynomials if you need to. Do the long division. Then when the degree of this expression down here is less than the degree of this expression over here, then you're done. Then this rational function here is the quotient plus the remainder over the divisor. So it's this plus the remainder over the divisor. Now, this remainder over the divisor can be handled with partial fraction decomposition. So we factor the denominator as much as possible. We state the right partial fraction decomposition, multiply by the LCD to get here. And then because we're solving for two values, a and b, we're going to choose two x values to substitute into this equation. When we do, we're going to get two equations and two unknowns in general. But if we choose the x values that cause these factors to be 0, then one of those terms will completely reduce and we'll just have one equation and one unknown. So whenever you have linear non-repeated factors in that denominator, this is the easiest way to go. Choose the x value that causes that linear factor to be 0, and that immediately gets us b. Get an equation involving b, you can solve for b. Then we choose the x value that would cause this factor to be 0. Then you immediately get an equation involving a that you can solve for a. Now, once you have your a and b, you substitute those into the form of the partial fraction decomposition. It was a over x minus 1 plus b over x plus 2. I just sub in the a equals 1 and the b equals 1, and we antidifferentiate. We have a power rule, the antiderivative of a constant with respect to x here. This is a very simple u sub, and that's a very simple u sub. Notice that we ended up with just natural log of the absolute value of x minus 1 here, and the natural log of the absolute value of x plus 2 here. That will always happen provided that the coefficient of x in the denominator is just a 1. So we would end up with the constant in the numerator times the log of the absolute value of the denominator, provided that this is just x plus or minus c in the denominator. But if you want to be sure, do the u substitution for this piece and this piece, and you'll see from the u substitution, they end up with just a constant over u, and the antiderivative of a constant over u would be that constant times the natural log of the absolute value of u. Don't forget to back substitute, and then you're done. I hope that helps. Please let me know if you have any questions.